Today we're going to talk about 2.5 enzymes. So from what we've talked about so far in 2.4, when I ask the question, what is an enzyme, at least you should be able to come up with the idea that it's a protein. So our first understanding is enzymes have an active site to which specific substrates bind. So on this slide here, I'm going to go through each of those vocabulary terms because I'm sure there was a few you hadn't heard before, like active site or substrate. So if you look at this picture here, every enzyme has a specific substrate that connects with it. Okay? So the enzyme will only work with that substrate. So a substrate is a reactant in a biochemical reaction. So it's going to be one of those molecules or polymers that we've talked about. So for example, lactose could be one, which is two glucoses, or a galactose and a glucose together. So the substrate could be lactose. And then the enzyme is a protein, which is going to act as a catalyst for this biochemical reaction. So it's going to break down that substrate, or it's going to be used to help build that substrate and connect it to other things. So it could be anabolic or catabolic. But either way, this enzyme is going to be a catalyst, which is going to means to make something go faster and speed up. So it's going to speed up this biochemical reaction to get more product faster. So here you can see that it looks like a lock and key, that this substrate fits perfectly to this enzyme. So these two know each other, and they will, when the substrate approaches the enzyme, they will react. The edge here of the enzyme, where the shape is, like the keyhole, we could say, is polar, and so is the edge of the substrate. So they will want to bind together. We call this location on the enzyme where the substrate is going to attach the active site. So the active site is the region on the surface of an enzyme to which the substrate will bind and which catalyzes the reaction. When they are together and connected, we call this the enzyme-substrate complex. Once a substrate has been locked into the active site, the reaction is going to catalyze, so it's going to speed up that biochemical reaction. So here you can see they are connected together, the substrate and the enzyme, and then when the reaction is done, the enzyme is going to release the substrate in its new form. So now you can see the substrate's been broken down into two separate pieces. So in this case, if this was originally a lactose substrate, this would now be a glycogen and galactose and a glucose molecule. So you make sure you know these words: substrate, enzyme, and active site, an enzyme-substrate complex. So the next understanding is about how enzymes, catalysts, involves molecular motion and collision of the substrates with the active site. So we call it the induced fit model because it's not truly a lock and key. So notice that this substrate is not the same shape as this active site here. But when the substrate approaches and as the substrates are colliding with the enzymes, the enzyme recognizes the substrate and it starts to do something called a conformational change. Think of the word conformational as like it's confirming that this is the substrate, okay? That it needs to do this reaction or that it's going to help do this reaction. So notice the shape changes and now the two polar regions can connect and bond together. When the reaction is over, the enzyme is going to release the substrate and it's now going to be in its new form, so into the products that it was created into. So this original substrate's been broken down. This is a catabolic reaction into two different monomers. So there's going to be when it connects like this, it alters the stability of the bonds in the substrate, which then can allow for it to further be broken down into other forms. Okay, our next understandings, there's two here. So temperature, pH, and substrate concentration affect the rate of activity of enzymes. And then also enzymes can be denatured. So let's talk about that. So the concentration of a substrate, so concentration means how much of a substrate might be in a solution, for example, can affect the rate of activity of an enzyme. And we call this saturation. When there's too much of a substrate in a solution and there's only so many enzymes, the enzymes become distracted or filled, right? There's not enough active sites available for the amount of substrate in the solution. And we would say that the enzymes have become saturated. So you'll notice that the rate of activity starts to plateau. It doesn't so much decrease and drop down, but it'll plateau and not go any faster. But sometimes enzymes can also be damaged. So remember we talked about how proteins like to be in a specific environment. And if they're not in that specific environment, they can become denatured, which if you remember from the 2.4 lecture means they lose their shape and they start to unfold and they cannot be folded back. So they lose that tertiary structure. And once that tertiary structure is lost, the protein no longer will have its shape, which means it can no longer do its specific function. So the two things that can denature an enzyme are temperature and pH. So if you notice here in this example, this is a crystallized structure of a protein, and you can see it at different temperatures, and you notice that the shape changes, and by the time it gets to 125 degrees Celsius, it's pretty much unfolded and lost its tertiary structure. So it would then be called denatured. So one of the skills you're going to have to be able to do is either draw or interpret graphs that are representing enzymes' rate of reaction. So these two graphs are showing substrate concentration information. So the first one here is showing how much product is formed from the substrate over time. And each of these lines are representing different amounts of substrate concentrations. So what you should know is normally what you're going to see is a negative correlation when it comes in terms of increasing substrate concentration. So as the substrate concentration increases, you're going to be seeing over time, you're going to be seeing it start to have less product formation. So I'm assuming these first lines up here, there was less substrate at those times, so they got more product from it. But as more substrate was added, it was decreasing how much product information or product formation occurred. So I bet this line here had a lot of substrate. If it was to be labeled how much was there, there'd be too much and it was saturated. This line graph is showing you that the substrate concentration is on the x-axis and the rate of reaction or velocity is on the y-axis. So notice that as the substrate concentration increases, the rate of reaction decreases, or plateaus, we shouldn't say decreases. So it was going up, 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 and then it just starts to slow down here. So you would need to be able to recognize this idea on a graph, or be able to draw one, given information. Here's one showing the effect of pH on enzyme activity. So every enzyme has an optimum, that's another word you want to be used to using, an optimum pH, so one that they like best, that they're going to get the most product from their substrate. So this point here at the top on this bell-shaped curve would be its optimum pH, because you can see it has the highest rate of activity. And pHs can be anywhere from 0 to 14. So this isn't numbered right here on this graph, but if it was, let's say it was 7, that would mean that this enzyme likes to work best at a pH of 7. But anything else on either side, you're going to get less product formation. And if it's even at the farthest ends on this graph, this would show that the protein was probably, or the enzyme was denatured, because you're not getting any activity. Here's a graph showing the effect of temperature on enzyme activity. So here you can see the temperatures on the x-axis and then the rate of reaction of the enzyme. So how much product it's forming over time. Notice that the optimum would be here, so around 40 degrees Celsius, maybe a little bit over. Most enzymes like that temperature, and anything on either end can start to denature the enzyme, and there's going to be less of a rate of reaction. So anytime you get to this point here where it says 60, and it's now the line has hit 0 again, that would mean that that protein has been officially denatured and it's permanently damaged. So all enzymes have an optimum temperature that they work best at and an optimum pH. So another thing that we've learned through the years in technology is how to immobilize enzymes. And so a lot of industries do this in order to make different products through biochemical reactions faster, and they can be able to reuse the enzymes by doing this. So the way they do this is the enzymes attach to an inert, which means something not mobile, so inert, insoluble, so it can't dissolve, molecule, which makes the enzyme more resistant to changes in temperature or pH. So it's going to be able to handle any changes that occur in that industrial environment, and it's going to still be able to make the product that was intended to be created. So the enzyme's also easily separated from the substrate and can be used again over and over again. So economically, this would help the business save money too. So there are a couple different ways you can immobilize an enzyme, but the basic idea you need to see is that it's going to restrict the enzyme from being mobile in a fixed space. So here's an idea of the enzymes being trapped in droplets or in this matrix grid type shape. This picture here on the bottom is an example of immobilized enzymes that are in calcium alginate beads that can be used in like laundry detergent processes, for example. It would be an example of an encapsulation. But here are the different ideas. So you can do like a matrix idea, which is over here with entrapment. You can do a covalent bond where they're attached or attracted to some sort of a support molecule. Cross-linkage, which is creating bonds between these enzymes. And absorption as well. So you can see here there's a support that it's attached to. So all of these have a way to immobilize the enzyme so it doesn't go anywhere, and they can remove it and use them again from whatever biotechnology or industrial process it's being used for. Here are some ways that it can be used in industry. So detergents is an example, which contain protease. So anytime you see ase at the end of a word, that's the enzyme's name. So like lactase, protease. Protease and lipase to help break down proteins and fat stains in our clothing. Enzymes are used to break down the starch and grains, for example, in biofuels that can be combusted. In textile industries, so clothing industries, can help in the processing of fibers, for example, polishing cloth to make it appear more shiny. In the brewing industry, so for making beer, enzymes can help a number of processes, including clarification of the beer. In medicine and biotechnology, enzymes are widely used in everything from diagnostic tests to contact lens cleaners and to cutting DNA and genetic engineering. In the food industry, it can be used with making fruit juices. Pectin is what's used to increase the juice yield from the fruit. Fructose is used as a sweetener, can be converted from glucose by isomerase, and rennin is used in cheese production. There's also enzyme used in paper production for creating paper from the pulp of wood. So one application that you need to know about is lactose intolerance. Okay, so there's lots of people around the world who are intolerant to lactose. They cannot digest this milk sugar that's being created. So lactose intolerance is the inability to digest lactose because of the lack of the required enzyme lactase in the digestive system. So your body is not producing enough of this enzyme. Here you can see the molecular structure of lactose. Then if you were to add a water molecule, and then that would create lactase, the enzyme lactase would then be used with lactose. So lactose is the substrate, lactase is the enzyme, and that's going to create a galactose molecule and a glucose molecule as the product. So this would be a hydrolysis reaction, which is a catabolic reaction, so it's breaking it down into smaller pieces, this enzyme reaction. So your body's not producing the lactase to do that. If you look at this map, you can see the frequency of lactose intolerance around the world. So if we look here at South America, it's all pretty much in the same range, but 61% to 70% of people are lactose intolerant. It's actually very common evolution-wise. Normally, when we think about it, all adults are going to have intolerance to some extent. But if you notice over here, Australia seems to be pretty special in that they're falling in the 0 to 10% area. But if you look here in Africa, in the southern portions or southern half of Africa, there is a high amount of lactose intolerance, as well as in Asia. But also notice babies are all going to be in that 0 to 10%. There are some babies who are lactose intolerant, but that's very rare because this is the food source that they're going to have when they're young. But then once we grow into adults, we start to become more intolerant to it, and we produce less lactase naturally. But some of us just really love milk and dairy products, and so lactose-free milk has been invented. Lactase is obtained from an artificially culturing a fungus, and the fungus grows naturally in milk, where it uses lactase to hydrolyze lactose into glucose and galactose. So scientists have discovered this fungus that grows on milk, and they basically, what these biotechnology companies do is they culture this same type of fungus or yeast, and they extract the lactase from that yeast, and then they purify it for sale to food companies. And then so food companies are going to add that lactase to their milk product so that it's going to be already broken down into glucose and galactose. It makes the milk a little sweeter in taste, but it's more easily digestible for those people who are lactose intolerant and still crave milk products. So they get the DNA from this fungus, and then they grow it in this yeast, is what they're doing. This strain of lactase, or this enzyme lactase in the yeast. All right, so we're going to stop there. Please write down any questions you have in your notes, and we're going to talk about them at the beginning of next class. And please submit your notes on ManageBack. Have a great day.